Today we're going to be talking about circuital laws. And the first law that we're going to be talking about is Ohm's law. So way back in the late 1830s, this German physicist by the name of George Simon Ohm started doing a bunch of experiments. And I'm going to describe his experiments to you here real briefly. So he took a network and it was a two-terminal network under test. So here is our network under test. And he electrically excited this network. And what he did was he measured the voltage drop across the network. I'm going to call this voltage V test. And he measured the current flowing into the network, which I'm going to call I test. This is exactly what I had you guys do at the end of our last class meeting. This was mini lab number 1. So most of you guys hopefully got through everything and plotted your graphs and all that kind of stuff on Excel. What do they look like? Lines, right? So if you followed the directions, you would have had current measured in milliamps on your vertical axis and voltage measured in volts on your horizontal axis. And you should have gotten a curve that looked something like this, right? So what George Simon Ohm found through his experiments is that there is a linear relationship between voltage and current. And he describes this linear relationship as resistance if we look at it in one way, and conductance if we look at it in a different way, right? So the slope of this line right here is the ratio I test divided by V test, and we give that special symbol G for conductance. And then the inverse of that slope. So if we were to swap the graph, slope to the -1 power is V test over I test, and we call that resistance, right? So Ohm's law effectively says that the voltage drop across a network under test is equal to the current flowing through the network under test times the resistance of the network under test. Or we could express it as the current flowing through the network is equal to the voltage times the conductance. Both of those are technically Ohm's law. 99.9% of the time, we're going to use this representation. As a point of fact, we're not really going to mention conductance much other than today and in a couple of your homework assignments until you're significantly later on in your electrical engineering career. There are certain aspects of transistor amplifier analysis that are a little bit easier to do dealing with conductances. Once you get into transmission line theory, you'll see conductances and all that kind of good stuff as well. Ashton, you worked professionally as an electrical engineer for about 5 years. How often did you deal with conductances? Pretty much never. And that's pretty much the case as well. Most of the time, we're just going to deal with resistance, okay? So just to tie these things together, I want to mention that resistance is simply the inverse of conductance and vice versa, so that if you are ever dealing with conductances, you can always just take the reciprocal of it to give yourself resistance, treat it as a resistor, and then move on about your day without losing any information whatsoever. So pretty much don't use conductances. Certainly not in this class. So resistance R has units of ohms, where an ohm is simply 1 volt per amp, and conductance G has units of Siemens, like the German company, that has units of 1 amp per volt. Resistance can be defined as the difficulty at which current passes through a medium. So effectively, the larger the value of the resistance is, the harder it is to pass current through it. And since conductance is simply the reciprocal of resistance, conductance can be thought of as the ease at which current passes through a medium. So we can use Ohm's law and our power relationship to develop some alternative ways in order to measure power across at least resistive elements. Let me see what's going on in chat here. Thanks. I'll turn it off just so you're not getting a great view of the ceiling the entire time. So using Ohm's law and our power relationship, we know that P is equal to I times V. This can be alternatively expressed as V squared divided by resistance, or I squared multiplied by resistance, in terms of if we have a resistance given to us, right? So instead of needing to know both the voltage and the current, now we only need to know one of those two quantities, whichever one is easier will get the job done. In terms of conductance, P is still going to be equal to I times V, but now we're going to have V squared times G, or I squared over G. Right? So we've got all of these mathematical relationships concerning resistance and conductance. Now let's talk pretty briefly about what it is that resistance does. So one of the first circuits that you guys ever built way back in Engineering 120 was something like this, where you had a 5-volt supply from your Arduino. So this was actually probably one of your digital output pins that you were commanding to be at 5 volts, connected in series with a resistor. By the way, memory serves me correctly, this would have been either a 220 ohm resistor or a 470 ohm resistor. Anything larger than that, and your LED is kind of dim. And then we had, trying to remember, our LED, like so, making sure I'm putting the negative polarity terminal of the LED on the right place so I don't look like a jackass. All right, so what was the purpose of the resistor in this circuit? What happened if you didn't put the resistor in and you just applied all 5 volts across your LED? Got really, really bright for a split second, and then it ceased to work forever, right? So the resistor was there as a current limiting device to make sure that the LED effectively didn't overheat and burn out. That's all a resistor can really do, okay? All a resistor is capable of doing is converting electrical energy into heat energy. That's completely it, okay? So let me write that down. Resistors convert electrical energy into heat. So if resistors are only capable of converting electrical energy into heat, can they store energy? No, absolutely not. A resistor can never store energy, which means the power that is absorbed by, or effectively resistors are only capable of absorbing power. They can never supply power to any other part of a circuit or anything like that. So anytime you're calculating any kind of power related quantity for a resistor, it is always, always, always going to be a absorbed quantity. Ohm's law tells us that if we ever have, let's say, a voltage drop across a resistor that's negative, the current has to also be negative in order for our absorbed power to always be positive and things like that. Okay. So we are actually going to modify Ohm's law very, very slightly here to help us sort things out. So if I have a resistor, by the way, the schematic symbol for a resistor, which you all should have seen by this point, is this line with some squiggly bits there. So if we have a resistor and we have the voltage drop across the resistor like so, so positive polarity on the left, and the current I is flowing into the positive polarity terminal, then we are going to use Ohm's law as V is equal to I times R. However, if we have this situation where we have our resistor, now let's put the positive polarity terminal on the left and the current flowing into the negative polarity terminal. Let me define this as R. We are going to say that V is equal to negative I times R. So when we're applying Ohm's law, the terminal that the current flows into governs what sign our Ohm's law equation is going to have. The current's flowing into the positive polarity terminal, Ohm's law gets a positive sign. Current's flowing into a negative polarity terminal, Ohm's law gets the negative sign. This is a place where I see a whole lot of students make a whole lot of mistakes early on. So I'm trying to emphasize these are the rules that we are going to be abiding by throughout the duration of this quarter. Okay. This goes back to the passive sign convention, and it also goes to the fact that, again, resistors can never supply power. They can only absorb power. All right, so I want us to talk very briefly about the resistance of a wire. Okay. This is an equation that, at least when I was teaching Engineering 121, used to be given to you guys. I'm not sure if it still is. The resistance R is equal to rho sub E times L over A. So this rho sub E right here is what's called the resistivity of a material. And it's usually measured in ohm meters or ohm centimeters. L is just the length, arbitrarily measured in meters. And A is the cross-sectional area measured in meters squared. So if we had a section of wire making it a very long section of wire. The axial direction would be the length. And this bit right here would be the cross-sectional area A, and then the material that the wire is made of will contribute its resistivity to our equation, right? Or I'm making an assumption here that we're passing current down the length of the wire as opposed to down through the top of the wire and out the bottom like some sort of jackass. We're using the wire for its intended purpose, sending electricity across some distance. The wire that we've used in developing all of our circuits or putting together all of our circuits to this point is 22 gauge wire. So I want us to calculate the resistance of a section of 22 gauge wire, okay? So I don't remember what the resistivity of copper is off the top of my head, nor do I remember what the diameter of 22 gauge wire is. I'm just going to look those things up. Misspelled it, but Google should be able to figure it out. There we go. 1.77 times 10 to the minus 8 ohm meters, or 1.77 times 10 to the minus 6 ohm centimeters. All right. So let me write that down. So 4 away. 22 AWG copper wire, row E, 1.77 times 10 to the, minus 8, not minus 18, ohm meters. And .22 gauge wire has a diameter of 0.6426, so let's call it 0.643 millimeters. Let's say, just for the sake of argument, that our length of interest, how long is the wires that you guys use to put your circuits together? Ballpark it. The wires that you guys have used previously in constructing your circuits. A couple of inches max, right? So let's say 10 centimeters would be the longest length. That might be a little shorter than the longest length, but it's not going to be by much. Okay. So I want us to figure out what the resistance of a 10 centimeter long section of 22 gauge copper wire is. So our resistance, R, will be equal to 1.77 times 10 to the minus 8 ohm meters times our length of 10 centimeters. And since I have ohm meters times centimeters, I need a conversion factor here. So there are 100 centimeters per meter. So since my wire has a circular cross section, that's going to be pi times the radius squared, or pi over 4 times the diameter squared. Since we have diameter, let's use that. I'm trying to get rid of meters. Nope. Actually, no, you're right. I'm going to have meter squared over meter squared. Thank you, Ashton. You're correct. Yeah, but I don't want to do that. Thank you. All right, so now I'm going to have meters squared, and then I'm going to have to convert. Okay, thank you. Pi over 4 times 0.643 millimeters quantity squared times 1 meter is 1,000 millimeters squared. Got all of them right this time? Thank you. Let's throw this into our calculators. So 1.77 times 10 to the -8 times 10 over 100 divided by pi over 4 times 0.643 squared times 1 over 1,000 squared. And I get 0.00545 and some change ohms, or about 5 milliohms. Why am I bringing this up? Well, what is the smallest resistor that you guys have used in putting together a circuit in your previous classes? Probably that 220 ohm resistor. So this guy is thousands of times smaller than that. So the wires, while they do have some finite amount of resistance, it is so small as to be considered negligible. So for all intents and purposes in this class, we are going to assume that wires have no resistance whatsoever, which is what you've been doing up to this point, but now you know why you can do it, okay? So that brings me to the concept of short circuits and open circuits. So a short circuit as an element is really just going to be a section of wire in some greater circuit, okay? The resistance is going to be 0. And since the resistance is 0, Ohm's law tells us that the voltage drop across this section of wire must also be 0. So anytime we have a short circuit, the voltage drop across that short will always, always, always be 0. We're going to use this in our circuit analysis very, very regularly, okay? On the flip side of that, we have an open circuit, which looks like a lack of wire, for lack of a better term, or just a set of open circuited terminals, right? So there's no conducting path. The resistance of an open circuit is infinitely large. This isn't particularly true, just like the resistance of a short circuit isn't particularly true either, right? If I apply a large enough voltage across nothing, I will cause dielectric breakdown to happen and electricity will flow. It will be dangerous. There will be sparks and all that kind of stuff involved, but I can force current across a long distance of nothing, air, vacuum, whatever you want to call it, if I put enough energy into it. You're not going to do anything dumb like that in this class, but it is technically possible. But we're going to consider, for the purpose of this class, for an open circuit to have an infinitely large resistance, which means the current flowing into that open circuited branch is 0, and the voltage will just be whatever it needs to be. All right. So we've talked about Ohm's law, defined resistance, conductance, talked about how resistance is dependent not only on the geometry of the system, but also the material of the system, covered short circuits, covered open circuits. Anybody have any questions regarding Ohm's law? Yes, ma'am. Mhm. Not at all. Nope. So up here in my definitions for if current is flowing into the positive polarity terminal, we use a positive sign, and current flowing into the negative polarity terminal, we use a negative sign. I did not specify the sign of the current or the voltage. So this works all the time. Yeah. If a negative current is flowing into the negative polarity terminal, you will find out that the voltage must also be negative for everything to work out correctly. Yes. Any other questions? All right, so one of our three circuit laws down. Now let's talk about Kirchhoff's voltage law. So Kirchhoff's voltage law simply states that the sum of all of the voltage drops around any closed path must equal to 0. We're going to put this into practice here in a couple of moments, looking at things by like what I mean by closed path and all of that kind of good stuff. But let's talk about this conceptually really quickly. Okay. So in class on Friday, we talked about how voltage is just a difference in electric potential between 2 points, right? And we also talked about how voltage is just the work done per unit charge, moving charge from one point to another, okay? So Kirchhoff's voltage law is all about energy transfer in a system, and saying that the sum of all of the voltage drops around any closed path is the same as saying the total amount of energy transferred in the system must be equal to 0. So Kirchhoff's voltage law is really nothing more than the law of conservation of energy in circuits form. That's literally all it is. It can never be violated. It will always, always, always work. Okay. So the great thing about it working around any closed path is that we can be pretty imaginative about the paths that we can use in order to figure things out, okay? So in its most simplistic form, we can use Kirchhoff's voltage law to find voltages. So I want to define a circuit here. So let's say that I have an 8-volt source like so. A resistance over which I measure a 3-volt drop. A resistance over which I'm trying to find the voltage. Just for the sake of argument, let's put the negative polarity here on the left. I'm going to call this Vx. Let's put a 1-volt drop there. So the first thing that I want us to do is to just figure out what Vx is and kind of learn the rules on how to apply Kirchhoff's voltage law. So in order for me to form a closed path, that simply means that I need to start and end at the same point in my circuit, right? So how I like to treat this is I arbitrarily choose a direction. So would you guys prefer to choose clockwise or counterclockwise around this path? Clockwise, okay? So we're going to be going around this path in a clockwise direction, and I'm going to start from the bottom left-hand corner and then just go around. Anytime I see a negative polarity terminal first, I'm going to put a negative sign in. Anytime I see a positive polarity terminal first, I'm going to put a positive sign in. So my Kirchhoff's voltage law equation for this simple circuit would look like, so let me write this down, negative 8 volts, and it's negative 8 because I see the negative sign first, starting from the bottom left-hand corner. Then I see the positive polarity terminal of that 3-volt drop, so plus 3 volts. Then I see the negative polarity terminal of the voltage Vx, then the positive polarity terminal of the 1-volt source, and then I just have that wire at the bottom, which is ground, which is, there's 0-volt drop across the wire. So I'm just going to set this equal to 0. I've taken into account all of my different elements in the circuit. And if I rearrange this guy, I'll find that Vx is equal to negative 8 plus 3 plus 1. Is negative 4 volts. If I had chosen to go around this circuit in a counterclockwise direction, what result would I get for Vx? Negative 4 volts, the exact same thing. It does not matter which direction we choose to go around the loop in. I'm going to get negative 4 volts regardless because the polarity I have chosen for that voltage Vx, that's it. If you'd like me to prove that, I'm happy to do it. Let's do it in blue. Okay. So I would have negative 1 volts plus Vx minus 3 volts plus 8 volts is equal to 0, leaving Vx on the left-hand side and moving all of the other stuff to the right-hand side. I get Vx is equal to positive 1 volt plus 3 volts minus 8 volts is still negative 4 volts. So the direction that we choose for our Kirchhoff's voltage law path does not matter. The only thing that matters is our polarities. Those are critically important. Okay. Now I'm going to do something that's going to annoy the hell out of you guys. Yes. Yep, we're just picking one. In fact, what I'm about to talk to you about is the whole, we don't actually need current to flow at all. So, for example, let's say that I defined the voltage drop Vy here across the middle of the circuit. This is the voltage drop between 2 points, so it's perfectly fair game, but there is most decidedly no current flowing down through that middle area, right? Any current that's flowing in this circuit is either circulating clockwise around the perimeter or counterclockwise around the perimeter. There is definitely no current flowing through the open circuit in the middle, but we can still observe a voltage drop. So my path for this guy might be this path. It could alternatively be this path, and we could change the direction on either one, but we can still apply Kirchhoff's voltage law to figure out what this particular voltage is. So I'm going to use the green path to solve for Vy. So since this is a separate thing, I'm going to put a line under it. So starting from the bottom left-hand corner and following that green path around, we would have negative 8 volts plus 3 volts plus Vy is equal to 0. So Vy is going to be equal to, excuse me, this thing keeps moving on me and it's ticking me off. 8 volts minus 3 volts is equal to 5 volts. And if I went in the opposite direction of my green path, I would still get that exact same result. So, cannot emphasize this enough. We do not need to worry about current whatsoever when we are applying Kirchhoff's voltage law specifically, okay? Kirchhoff's voltage law says the sum of the voltage drops around a closed path is equal to 0. Nowhere whatsoever does it mention current. That being said, we can use Ohm's law in connection with Kirchhoff's voltage law in order to determine currents and things like that. So let's look at something like that. So here's a 7-volt source. Let's make this a 10 ohm resistor. Two ohm resistor over which we're going to define a controlling voltage. So this will be negative Vx, or excuse me, Vx with negative polarity on the left. And then let's put a dependent source here. Let's make this 2Vx, like so. And what we're going to wind up doing is using a combination of Kirchhoff's voltage law and Ohm's law in order to solve for the quantity Vx in this circuit. Let's just put Vx is equal to question mark to remind us of what we're solving for. All right, so I'm going to apply Kirchhoff's voltage law to this circuit. I'm going to start from the bottom left-hand corner, and then I'm going to follow a path either clockwise or counterclockwise. So pick clockwise or counterclockwise. Clockwise, all right. So the first thing I see is the negative polarity terminal of the 7-volt source. So I have negative 7 volts. Then I see a 10 ohm resistor, okay? And it doesn't have a voltage drop associated with it. So we are going to have to make one up. We get to choose whether the positive polarity terminal will be on the left or the right. So let's see, Trilby, pick left or right? Left, okay? So this is a decision that we have made. I'm going to call this voltage V10, representing the voltage drop across the 10 ohm resistor, positive polarity terminal on the left, because Trilby suggested putting the positive polarity terminal on the left. So that's going to be plus V10 minus Vx plus 2Vx is equal to 0. We can very obviously see that negative Vx plus 2Vx is just going to look like positive 1Vx. So let's go ahead and simplify this a little bit. So I'm going to call this V10 plus Vx is equal to 7 volts. And if my algebra is wrong, please correct me because I have a tendency to screw up simple algebra. Anybody have beef with this simplification? All right. So I wrote the equation in this way so that we can very obviously see that we have a little bit of a problem in as much as we have one equation, but two unknown quantities. So we're going to figure out what those unknown quantities are by using Ohm's law, okay? Or a better way to put this is we're going to represent these two unknowns with a single common unknown quantity, okay? So because we chose to analyze this circuit in a clockwise fashion, I am going to arbitrarily say that our current, let's just call it I for the sake of argument, is flowing clockwise in this circuit. I don't have to do this. I'm just doing it because that's the direction we've already assumed. Okay. Using Ohm's law, I can now express my resistor voltage drops in terms of that current I. So what would the voltage drop V10 be in terms of that current I times 10 ohms. Okay. Positive or negative? Positive. Why? Because the current's flowing into the positive polarity terminal. Okay. So V10 will just be I times 10 ohms. What will Vx be in terms of that current I? That's a 2. Sorry for my penmanship. Negative I times 2 ohms. It gets a negative sign because the current is flowing into the negative polarity terminal. Very, very important that we keep track of things like that, right? So we can substitute these relationships in. So V10 is 10 ohms times I plus Vx is negative 2 ohms times I. And this will be 7 volts. So we have a common factor of I. And then out here, we're going to have 10 minus 2. So that's going to look like 8 ohms times I is equal to 7 volts. I would then be 7/8 of an amp. And so Vx, the thing that we were originally trying to solve for, would be negative 7/8 of an amp times 2 ohms is going to look like negative 7/4 of a volt. Anybody have any questions? So this is probably your first problem involving a dependent source. I'm trying to not make it ludicrously terrifying because it doesn't really have to be, right? As long as we're just paying attention to signs and directions and all that kind of stuff, this is really as hard as circuit analysis needs to be. All we're going to be doing from here on out is lots and lots of this, just with bigger and uglier looking things. All right, so now we've talked about Kirchhoff's voltage law, laid the groundwork for the rules for using it, worked a couple of different examples using it to find both voltages and currents and stuff like that. From here, we could also find powers and all that kind of thing if we were so inclined. Does anybody have any questions about this before I move on to Kirchhoff's current law? All right. So Kirchhoff's current law is interesting. Okay, well, I'll circle back around. I just thought about that. Kirchhoff's current law is interesting because there are really 3 different ways that we can think about it, and they all mean effectively the exact same thing. Okay? So I'm going to draw a portion of a network here. Where we just have 5 wires all connected to some central node point. Okay. I'm going to arbitrarily choose some directions for my currents. So let's say that this is current I1 flowing in this direction. Here's I2, I3, I4, and I5. So our first way to represent Kirchhoff's current law is probably the one that you guys are the most familiar with. And that is that the sum of the currents entering a node must equal the sum of the currents exiting or leaving the same node. So if I were to write a Kirchhoff's current law equation using this form of Kirchhoff's current law, I might put all of the positive currents, or excuse me, all of the currents that are entering the node on one side of an equal sign and all of the currents that are exiting a node on the opposite side of the equal sign, and then just go from there, right? So since I1 is entering the node, I'm going to put it on the left-hand side over here. I2 is exiting, so I'm going to put it on the right-hand side. I3 is exiting, so I'm going to put it on the right-hand side. I4 is entering, so it goes on the left-hand side of the equal sign. I5 is exiting, so it goes on the right-hand side, and I'm done, right? The currents that are flowing in, I1 plus I4 equals the total current flowing out, I2 plus I3 plus I5. This is, like I said, probably the version of Kirchhoff's current law that you're most familiar with, and I do still use it on occasion, but typically speaking, I wind up using one of the following two that I'm going to go over here, right? So our second representation is the sum of all of the currents entering a node must equal to zero. So this does not mean I1 plus I4 is equal to zero, because we can't neglect all of those other currents. We just simply have to recognize that if I2 is exiting, negative I2 is entering the node, right? So this would look like I1 minus I2 minus I3 plus I4 minus I5 is equal to zero. It is the exact same equation that we got for our first formulation, except that we moved everything from the right-hand side of the equal sign over to the left-hand side. So they are mathematically identical because these two things mean the same thing. Our third representation is the sum of the currents exiting a node must equal to zero. So in this case, negative I1 is exiting, positive I2 is exiting, positive I3 is exiting, negative I4 is exiting, positive I5 is exiting, set this equal to zero. And it's effectively the exact same thing as we got for our second equation, except that everything was multiplied by -1 because we're considering the opposite direction, which is exactly what we would expect given how currents work. So these are the three different ways that we can look at Kirchhoff's current law. Realistically, any of them work, or all of them work. And so you can use whatever one you're most comfortable with. That being said, nodal analysis, which is what we're going to get to about this time next week, I believe, will be a little bit easier on you if you start using option 3 there. The sum of all of the currents exiting a node must equal to zero. That's the formulation of Kirchhoff's current law that's used specifically in nodal analysis so that we avoid getting a bunch of spurious negative signs all over the damn place that we don't want to happen. Okay? You'll see what I mean by that when we talk. So for now, use whatever the heck you want. Once we get to nodal analysis, 99% of the time, you're going to start using option 3 there. All right, so let's work an example. So let's say that we have 3 amp current source, a resistor through which 2 amps of current is flowing, another resistor. Now we have a current source down. It's 8 amps. And we want to find this current flowing down through this unknown resistor, which I've called IX. So in order for us to apply Kirchhoff's current law, we need to decide on a node to apply it at. The circuit that I've drawn has exactly 2 nodes. What's commonly called a single node pair circuit, which just means everything is connected in parallel, right? So everything is connected between the top node and the bottom node. So do we want to apply KCL at the top or the bottom? Random. Top or bottom, completely arbitrary. Pick. Top, okay? So we're going to apply KCL at the top node. And are we going to use formulation 1, 2, or 3 of Kirchhoff's current law? 3, okay? So that means that any current that is exiting the top node will get a positive sign, and any current that is entering the top node will get a negative sign. So now I'm just going to work my way across the circuit from left to right. So that 3 amp source on the left-hand side is a current that is entering the top node. So it's going to get a minus sign. So we're going to have negative 3 amps. That resistor current of 2 amps is entering the top node. So it's also going to be negative. IX is exiting the top node. So it's positive. And 8 amps is exiting the top node. So it's positive. Set this equals 0 and rearrange things. So IX is going to look like 3 amps plus 2 amps minus 8 amps. Is negative 5 amps. Nope, negative 3 amps. Can't do simple math. Thank you, Ashton. You're going to do that a lot. Yeah, I can't do math with numbers to save my life. As you can very obviously see with this very simple addition that I just wildly screwed up. The process was right. I just can't do simple math. All right. So this is an application of Kirchhoff's current law, much like we saw with Kirchhoff's voltage law. We can also tie this into Ohm's law in order to figure out voltages and things like that. So let's look at another circuit here. And our goal is to find the current flowing through this 3 ohm resistor. So I'm going to call this IX. So we're going to apply Kirchhoff's current law. Anytime we see a single node pair circuit, that's probably going to be our first step. Right? So we need to choose top node or bottom node. Patrick. Bottom node, okay? So we're going to apply KCL at the bottom. And are we going to use formulation 1, 2, or 3? 3, okay. So currents that are exiting the bottom node are going to be positive, currents that are entering the top node are going to be negative. All right, so the first thing we see working our way from left to right is the 4 amp source. Because it's exiting, it's going to have a positive sign. So we're going to have 4 amps. Now we see our 6 ohm resistor, and since it doesn't have a current labeled for us, that means that we have to choose, right? So current through the 4 amp resistor, or excuse me, 6 ohm resistor, goodness. Janae, up or down? Down, okay. I'm going to call this I6 because this current is exiting. Sorry, because this current is entering the bottom node, it will have a negative sign. My apologies. And then IX is exiting the bottom node, so it's going to have a positive sign. Rearranging this guy, we're going to have negative I6 plus I3 is equal to negative 4 amps. And we have a similar situation where we have too many equations and only a single unknown, or excuse me, too few equations for the amount of unknowns that we have. Thank you. Need to be consistent. Thank you. Yep, they'll get over it. I'll make. Son of a bitch. Thank you. So as you guys have noticed, I'm going to make mistakes pretty often. If you see something, please say something, because I would much rather correct it than have you guys learn something wrong. Okay. All right, so we are going to have to tie in Ohm's law again, but we have a little bit of a conundrum here as well, because there are no voltages or anything like that labeled anywhere. Okay, so we are going to have to figure a couple of things out. I'm going to choose to put voltage drops across each of my resistors. So I'm going to do this in blue. So do we want the voltage to be on the top or the bottom? Positive polarity on top or bottom? Top, okay. So for now, I'm going to call this V6. And I'm going to call that guy V3. We're about to stumble into something important. Okay. If I were to write a Kirchhoff's voltage law equation around this path, what would I find? What would that Kirchhoff's voltage law equation look like, Hannah? Give me the KVL equation. Follow the blue path. Okay. Okay. So that means that V6 is equal to V3, right? So those are the same voltage. How are the 6 ohm resistor and the 3 ohm resistor connected to each other? Anybody? They're in parallel. Anytime we have elements that are connected in parallel, they are going to have the exact same voltage drop across them. So realistically, instead of expressing this as V6 and V3, a better way to do it would be to express it as a single voltage, which, for a lack of a better term, I'm just going to call V. And that's the voltage between the top node and the bottom node. It's also the voltage drop across the 4 amp source. Like I said, anytime we have things connected in parallel, they're going to share a common voltage. Just like we saw in that previous circuit, everything connected in series shared a common current. I just didn't point it out. All right, so let's use Ohm's law. And express the current I6 in terms of that voltage V. How am I going to do that? V divided by 6 ohms. Absolutely correct. Somebody else tell me how how I am going to express Ix in terms of that voltage V. So positive or negative? Because I believe that the current is flowing into the negative polarity terminal, which means I need to remember that negative sign, right? So it'll be negative V divided by 3 ohms. And now I can substitute those two relationships in. So negative I6 is going to look like negative V over 6 ohms plus Ix negative V over 3 ohms is equal to negative 4 amps. And I'm just going to get rid of all of these negative signs because they're bothering me. So that negative and that negative cancels that negative over here. So from this, I could see that V is equal to 4 amps. And let's see, I'm going to need to multiply by something here. Actually, it would be 4 amps divided by 1 over 6 ohms plus 1 over 3 ohms. Put that in my calculator. I get 8 volts. From that, Ix is going to be negative 8/3 of a minute. All right, so I want to work one last problem. That's going to require us to use Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law all together. I'm telling you explicitly, this is a problem that I put on the test last quarter, and it only had like a 20% correct response rate. Okay. So I'm giving you fair warning of the crap I like to put on exams. We have an undetermined source voltage that we are trying to figure out. Let's make this a 5 ohm resistor. This will be an 8 ohm resistor. This will be a 2 ohm resistor. This will be a 1 amp current source. We are told that the voltage drop here, I'm going to move this 2 ohms to the other side just to make it look nicer to me. Is 10 volts. I want us to figure out that voltage Vs. All we know to this point is KVL, KCL, and Ohm's law. Okay, so let's figure out, based on the information that we've been provided, what we actually know. Okay. A lot of noise coming from somewhere. Anyway, all right. So if I know that the voltage drop between, let me explicitly show this. This green node up here and this pink node down here is 10 volts. What can I use that to figure out? So if I have the voltage drop across the 8 ohm resistor and I have the resistor value of the 8 ohm resistor, what does Ohm's law tell me I can find? Current. Okay, so what would it be? Depends on what direction I define my current as. Let's assume we're looking at a current flowing down. Hit me with a number. 10 over 8, okay? So 10 over 8 or 5 over 4. We could also find the current flowing down through the 2 ohm resistor, right? What would that be? Somebody else. Yeah, 10 over 2 is 5 amps. So, using Kirchhoff's current law, I would argue that the current flowing through the 5 ohm resistor, let's call this IX, is just going to be the sum of that 5/4 of an amp plus that 5 amps plus that 1 amps using Kirchhoff's current law at the green node, right? Where the current's flowing into the node equal the current flowing out. So KCL at our green node, using formulation 1, says that our current IX is equal to 5/4 plus 5 plus 1. So let's see, 5 plus 20 plus 4 is 29 over 4. Anybody have a problem with that? All right. So if that current IX is equal to 29/4 of an amp, and it's flowing through a 5 ohm resistor, what can I figure out now? The voltage drop across the 5 ohm resistor. Let's call that voltage Vx. So Molly, what is Vx going to be equal to? What am I going to put in my equation? (29/4 of an amp), so that's our current. Five ohms. All right. Do I need a negative sign? No, because the current is flowing into the positive polarity terminal. All right. So 29 times 5, geez Louise. So 30 times 5 is 150 minus 5, so 145 over 4. So now that I'm here, how do I get Vs? Exactly right. So effectively, we're just going to apply Kirchhoff's voltage law around this path, right? So we would have negative Vs plus Vx plus 10. So Vs would be equal to Vx plus 10. So that would be 145 over 4. Is 185 over 4 volts. We just worked a problem here in, I don't know, 3-4-ish minutes that over or roughly 80% of your peers got wrong last quarter. Just using KVL, KCL, and Ohm's law. All right, so I think that is enough ranting out of me for today. If anybody has any questions, I would be more than happy to answer them. If not, please work on your in-class assignment. Once you wrap that up, you're free to leave it.